I'm just going to advance through the first slides because I've got a lot of slides and a lot of stuff and I want to get through quickly. So we'll just advance through this one, please. And the next one is, I think, the abstract. Well, people can read that and they can read that on their own. Next, please. Okay. Climate change is fairly important up north and it's going to impact permafrost. So we have a site up in Inuvik in the northwest of the Northwest Territories where we've had permafrost destabilization through a pit that has been dug for road gravel. And that's a ready-made experiment for understanding the impacts of rapid permafrost thaw. What has actually happened is that it has generated a lot of fairly nasty waters and that are impacting the surrounds of the pit. I haven't got much further than that at this point in time, but the idea is to look at the hydrogeochemistry to understand what permafrost thaw is going to look like from an infrastructure point of view. Because if every time you dig a pit you generate nasty waters, that's not going to be a very a positive scenario for development in the north. So exactly what's going on and why is something we're trying to identify. Next, please. Here's the pit. You can see it on the right of the photograph there. The pit was dug in 2012 to 16, I believe. The road was completed in 2017. It's called the Inuvik to Tuktoyaktuk Highway, otherwise known as the Tuk Highway, which is what everybody calls it because it's a whole lot easier. All the borrow pits, all the gravel pits in the area have real problems. They are, as you can see the subsidence even in the vertical photo there. And it's in many of them, not all, but many of them, rapid permafrost thaw is yielding high solute chemistry, some of them really problematic with lots of contaminants. Next, please. I'm not really going to go into the pit chemistry per se, except to say that it's been consistent ever since mining started. And even though mining stopped quite a few years ago now, it's really still ongoing. In the spring, it's dilute and the low concentrations, but by late summer, early fall, the concentrations are up around 3,500 microsiemens per centimeter. Sulfate and uranium and lots of other elements are well above water guidelines, aquatic health guidelines. So not nice and definitely worth investigating further. But I'm not really going to talk about that today because next slide. I really want to talk about the hydrogeology because we're doing a bunch of things that we're trying to understand what the actual waters are doing and why, and specifically there's quite a lot to talk about in this aspect. The pit is predominantly silty clay with minor pebbles, as you can see that from that from that photo. The gravels form lenticular, pebbly, probably complexly interconnected aquifers, and pretty much they're surrounded by pebble-free or very few pebbles, silty clays of just till origin. So it's essentially a till outflow with some ancient sedimentary aquifers generated by the stream flow. Next, please. As you can see, these aquifers don't necessarily form surface water flow. What they form is these linear depressions that essentially are where the advective heat flow from groundwater flow is essentially thawing permafrost and the whole surface is subsiding. And so it's really a groundwater dominant system that is basically remaking the landscape. Again, a beautiful sort of test site, but for the nasty waters. Next, please. So we're investigating them with three types of, well, the hydrogeology we're really trying to constrain with, and especially the seasonality of it, with these three types of sensors. The one on the left is a formation, so whole earth, total earth pressure sensor. It also has a pore water pressure sensor and a water temperature sensor. The one in the middle is just a pore water pressure sensor and a water temperature sensor. And the one on the right is permittivity, or volumetric water content is essentially what it is. Temperature and electrical conductivity sensor. Next, please. So these, we have groundwater walls. You can see with the orange cap in the background. In the actual aquifer itself, the aquifer is usually in the 1.2 to 1.6 meter depth range, whereas surrounding it, the actual depth of permafrost is more like half a meter or less. We put sensor wells across in all around these in the aquifer, around adjacent to the aquifer and distal to the aquifer too, to see what was how different, how well these sensors really perform to understand the hydrogeology. Next, please. So here's permittivity or volumetric water content, electrical conductivity, and temperature sensor data. Next, please. And what you see is the battery died in March. It didn't last, which was really unfortunate, but it gave us a lot of good data anyway. We got there in early May and we put the new batteries in, and away it went quite happily again. Next, please. So what's really, I'm going to go into this in a little bit of detail. These profiles are basically a 10-month, 11-month profile at different sites, some gravels in the aquifer, some adjacent to the aquifer and pebbly muds or just straight muds. What you see is that the depth-dependent 0 point, so when they all reached, is pretty much coincident with depth. So the deeper you are, the later you got to 0 degrees centigrade. Next, please. There's quite some noise in the shallow profiles, which is what you should expect because they're less insulated. So big changes in temperature in the overlying air mass is affecting those shallow sensors, but not the deep sensors, which is again what you should expect. Next, please. Lovely coherent thaw pattern, again, very nice, exactly what the theory should expect. And it's mostly, there's actually a few different things that aren't quite coherent, but within reason, that's what you're seeing. Next, please. One of the things you do see is an incoherent freeze-up pattern. So there's the arrow points to across where 45 centimeter deep sensor in pebbly mud, in the muds, essentially is crossed by a gravel, which is one of the aquifers. That the gravel aquifers basically all show these similar trends of shallower, less steep freezing. Directly implicates advective groundwater heat transport, is keeping these things from being as impacted by the overlying temperature. Next, please. And in the summers, beautiful uncoupled aquifer and aquitard records, again, suggest you've got pretty good aquifer flow. Next, please. So going into specific sites, on the left we have a pebbly mud at 45 centimeters. On the right we have a meter deep aquifer gravel. Next, please. The freezing shuts off the sensor current, as you see in the 0.45 meter. Next, please. Because ice doesn't conduct electricity. These are voltammetric measurements. And so the permittivity is always less than 0.1 in these situations, and the conductivity is always less than 0.01 or no reading at all. Next. You see something quite different in the aquifer gravel. Even by the end of late March, you've still not frozen the aquifer. Sorry, early March, you've still not frozen the aquifer. In fact, you're forming a brine. You're concentrating the solutes within that aquifer. Next, please. As said, it's still an aquifer. Next, please. And even when we start back in early May, you're on non-zero readings. So there's actually some current able to pass through that sediment, suggesting there is some free water. Next, please. There's a real difference in the way the aquifer thaws versus the way the non-aquifer thaws. Very rapid thaw in the aquifer. Next, please. What's really interesting about that is it actually happens, even though it's twice as deep, it actually happens earlier than the actual mud thaws. Next, please. There's really only one way I can think of explaining that, and that's advective heating. We're showing that these aquifers are actually very active, much more active than would have otherwise been expected. Next, please. We're going to go through this really quickly. This is another type of sensor. This is earth pressure sensor, so formation pressure. Next, please. what you see is that the formation pressure increases with depth. Again, exactly what you should expect. It's lithostatic pressure, it's recording lithostatic pressure. Next, please. Slight decrease during freezing. Not quite sure what that's due to. Really very small, but probably due to ice forming within the soil, providing a little bit of stability within the soil that takes pressure off the sensor. Next, please. And then there's this little, and in all of them, this little chunk, this little thing as it gets back. So it thaws and the pressure sensor returns to its pre-freezing time. Again, pretty much what you'd expect. Next, please. These sensors also have a pore water pressure sensor, and there's two main response types. Next, please. The first type is in the muds, not the aquifer, outside the aquifer. Next, please. You see decoupled responses between the pore pressure and the temperature. Exactly what you should expect during unfrozen times. They shouldn't be coupled. They're not related entities. Next, please. Not true for the winter period. You have strongly positively coupled responses between these two systems. Next, please. And you're getting very large pressure response for very small temperature changes. That says to me that you're getting a small volume effect. Next, please. I suspect the summer readings are, I'm pretty certain the summer readings are accurate for pore pressure. The winter readings in this system, I think, is a response to ice acting on the membrane within the actual sensor, and I don't think it's actually a representative of the pore pressure at the time. Next, please. In the gravels, you see something quite different. So you get pore pressure and temperature. Next, please. Sorry. Decoupled. They're decoupled throughout. Next, please. And the aquifer was always above -2 degrees C in pretty much everywhere. When we drilled this in early May, when it really should be frozen, it wasn't. There was plenty of water around. So this is really interesting that even though you're at -1, 2, you've still got a substantial amount of water that is producing high pore pressures. Next, please. So here these sensors, I think their response is reflecting local aquifer pore pressure. Next, please. That's really interesting. But if you actually put all these gravels together, you see quite different responses. In the consistent aquifer pore pressures during summer. Next, please. But very different in winter. That says to me that the aquifer is actually compartmentalized and probably not hosting substantive flow. Again, really interesting, a lot more to try and tease out of that, but that's not at all what people think of as happening in winter. People think of winter as shutting everything down. That's not at all true. Next, please. Obviously, the question, when did compartmentalization occur and how did it impact flow? I reckon we can get that from the data. I'm not quite sure how to do it quite yet. Next, please. So just to conclude, this is your scene on the left is sort of the outside the aquifer. You've got depth of winter freezing in your active layer. We've got sensors in there and drill holes, which basically tell us it's all frozen. And on the right, we have these aquifers sitting at the bottom of, sitting in and actually hosting a substantial flow in summer, advective heat transport, permafrost thaw. And that's where I think you must be deriving a lot of these nasty waters from. Next, please. And so we now have sensors. These sensors are standard sensors for non-permafrost areas. I think we've established that we can now use these sensors, these standard sensors up in the north. We've got a little battery issue to sort out, but that's not a big issue. But other than that, I think we've got some really, we've established that these are successful and we can derive a lot of really important data over the seasonal cycle from what these sensors tell us. Next, please. Interestingly, I think what we can say clearly is that there's at least 8 months of the year that we have aquifer flow. That's double what people would normally have assumed. It's substantially more than what you would expect given the temperature, the air temperature surrounding. Next, please. And unfrozen water and aquifers occur throughout winter. I was pretty certain of that beforehand, but it was sort of one of my hypotheses going in. But it is certainly, we've demonstrated that quite clearly. I think that's it. Next, please. Yes, that's it. I try to go as fast as I can. I hope I didn't leave too many people behind.